Hello, everyone. Now we're moving into chapter 6, which is our normal distribution. So we're going to start looking at these normal, first and foremost, is a continuous distribution. So in chapter 5, we spoke about discrete distributions. Now we're going to talk about continuous distributions. And in a continuous distribution, what we're looking at is if you look at the shape, they actually turn into smooth curves. They can look like that. They, of course, can be skewed. They can be lots of different shapes. They can have all kinds of weird things going on. These are all continuous distributions. So whenever we take that histogram and we kind of draw a smooth curve around it, what we're actually doing is we're creating a continuous distribution out of it. So down here on the axis, we have our x values. Now you'll notice something. Since there's infinitely many values here, if there's infinitely many values, what's the probability that we have any one value? So the probability, keep writing R, so the probability of any value x is actually 0 in continuous distributions, which kind of sounds funny. So instead of looking at probability distributions, we actually look at the probability density functions. Okay, so we're looking at probability density, and when we're looking at a probability of a continuous distribution, instead of looking at where this is, because that's not going to tell me anything, because I don't have a rectangle of size 1, because that's in discrete distributions. We have a rectangle of size 1. This is 1 unit, and then this is usually the probability on the side. So the area of this rectangle is our area, is our probability, because it's probability times 1. So just like that, what we have in continuous distributions is the area right here is our probability, say, from some x1 to some x2. Now that is not 0. And if you wanted a certain point, you could always say, so let's say I wanted the probability that something was 2. Well, that's going to be 0. But the probability that my variable is in a small area around 2, that is going to have a number attached with it. That is actually going to have a probability. Now, it may be small, it may be big. It depends on the distribution that we're talking about. So this is where we're going with continuous distributions. And we're going to start with the normal distribution. Now, the probability density function for the normal distribution looks something like this. It's kind of strange looking, I know. Don't worry about it. Don't get scared of it. We're not going to use it to use this. We can't use it. So we'd have to use calculus in order to use it, because of course, remember the area under the curve. Those of you who have taken calculus before, you would know that the area under the curve is the integration. Well, this isn't even something that can be integrated. It has to be numerically integrated with a computer, which is why we have normal tables and why your calculator has normal CDF. And you'll notice I said CDF, not PDF. We're not going to use normal PDF. It's not useful for anything except for graphing. So the parameters of the normal distribution are, there's a population mean, mu, that's right here, and there's a population standard deviation, sigma. The population mean is a location parameter. It tells me where on the x-axis the curve is. Is it here? Is it here? Is it here? Where is it? So all it does is all the different mu's do is move this back and forth along the x-axis. The population standard deviation, this is what we call the shape parameter. And the same basic bell-shaped curve stands, but some of them are tall and skinny. Some of them are short and wide. So this is what happens when we have different sigmas. Because as we know, standard deviation tells my variability. This doesn't look very variable, but this does. So that's what we're looking at when we're talking about the mean, and the standard deviation tells us these things about the normal distribution. So how do I know if a random variable is normal? Well, we say that they follow the normal distribution if their distribution has this basic shape. Now, of course, life isn't that perfect. Most distributions are not perfectly normal. They're approximately normal, which is good enough because most things are, and we have to call that good enough. So most things are approximately normal, and we like it that way. This one, notice this is centered at 10. That's our mean. Okay. So let's just kind of investigate a few normally distributed variables. Now, what I did here is I used a computer program to generate random numbers, and I wanted to make sure these random numbers were normally distributed. So I took a random sample of size 40 out of normally distributed random variables. And then I did a histogram of them. And I superimposed the normal curve. So this is the superimposed normal curve. Now, if you'd just seen this histogram, you'd be like, that doesn't look all that normal. It was. They were normally distributed variables. And look at this. My x bar is negative 0.0401, which is pretty close to 0, because this is the true mean. And my s is 1.2. It's a little bit off. So what happens, what do you suppose is going to happen if I multiply my number of chosen sampled by 10? Okay, this looks much better, right? Now we look much more normally distributed. And we go, okay, well, this is closer to 0, not that much closer. This is definitely closer to 1. This one's definitely much better, my standard deviation. Still pretty, not too close to the exact mean that it's supposed to be, but I'm getting there. And this definitely, the shape definitely looks better. So let's look at the next one. Here's 4,000. My shape definitely looks a lot better now. My x bar is 0.016, which is really, really close to 0. My s is 0.994, which is really close to 1. So the higher my n, the better samples I'm getting, the closer shape I'm getting to the perfectly, this is the perfect normal curve right here. And the better that I'm doing. So, of course, we're not going to get an infinite number of points in order to get this perfectly shaped curve anyway. So you can see how we'll call something normally distributed, even if it just basically looks like it. This doesn't even hardly look like it, but it is normally distributed. And this one you can really see it, and this one is wonderful. So let's look at these three normal distributions. And I talked a little bit about the mean being the location parameter and the standard deviation being the shape parameter. So you'll see these mu's, so this mu is -2. So you can see the center of this is -2. The center of this one is +3, and the center of this one is 9. So that's my mean. So whenever I'm going to go draw a normal curve, what I can do pretty easily is show where the center is. So I usually kind of start this and I go, there's my center. Now I want to look at what shape I am. Well, here my standard deviation is 1. Now, if we look 1, 2, 3 standard deviations on either side, that's where we really want to start getting close to the x-axis. So you really want to be not touching it, but just above it. So when you're drawing this, you want to draw just like that. So that's just your regular normal distribution. So what happens when I take my standard deviation by half? I'm less variable, right? So if I go 3 standard deviations away, that's 2.5, 2, 1.5. 3.5, 4, 4.5. So this is 3 standard deviations away. It's not as far. So remember, the area has to stay the same under the curve, so this has to be pushed up higher. It's kind of like, I want you to imagine a pillow. And if you take a pillow and you push the sides of it, the middle is going to go up. Or even a piece of paper. If I push the sides of a piece of paper, the middle is going to increase. If I push it together, if I put my fingers together more, that piece of paper goes even higher in the middle because the piece of paper, the size isn't changing. So let's look at this one. Now what happens when my standard deviation is 2? Higher the standard deviation, the more variable I get. So now to go 3 standard deviations away, I'm out here at 15. 1, 2, and I'm down here at 3. So you can see that's where I start to get close to the x-axis. So same idea. That's what we want to look at. So when we're looking at drawing these, we can look at 3 standard deviations away is where we want to get down here close. Okay. So here's another frequency histogram. This is for heights of women, superimposed with the normal curve again. So I want to remind you, if I look at any of these boxes, if I want the probability that somebody was between 67 and 68, so remember this is 1 by, if I take the area of a rectangle, 0.0735, that's 0.0735. That's the area of this rectangle. But if I want 2 of them, I'm going to take the area of this rectangle plus the area of this rectangle. So let's say I want from 66 to 70. Then that's going to be the area of all of these rectangles, which you can see the normal curve. If I just do the normal curve, I've got some things that are not in there, and I've got some left over. But I also colored an area that was not in a box. You can see, like right here, and right here, and right here. So if I want to approximate this area, or find the true area of women's heights, from 66 to, oh, I got 71 on here. From 66 to 71. Then I would take the area under this curve, go up here, take the area under this curve from 66 to 71. And that's how I could do that. So let's talk a little bit about some properties of the normal distribution. Number 1, first and foremost, it is a bell-shaped curve. So we have that. Second, the mean, median, and mode are equal and in the center of the data. So I don't know if you can read this little tiny print. 50% of the data are in this half. 50% of the data are in this half. Again, the curve is symmetric about the mean. So I could fold the normal curve right here, and everything would meet up perfectly. Fourthly, it's continuous. So for each value, there is a probability of There is a value of the probability density function. So even though it's very close to 0, and the density function is a little different than the probability, but each one of these has a value. So no matter which curve that you have, that just means that there's no continuous, just means that there's no jumps or anything in it. The curve never actually touches the x-axis. So you see down here, I got a mu plus 3 standard deviations away. It gets very close, but it never touches. It gets infinitely close to 0, but 0 is an asymptote. So it has a horizontal asymptote at y equals 0. So the total area under the curve equals 1. Now you think, well, how does that happen if the curve never touches the x-axis? Well, this area starts to get so tiny and infinitesimally small that it doesn't really add any. So the area under the total curve, this thing needs to go away. Okay. The total under the normal curve has an area of 1. And then here, the area under the normal curve that lies within 1 standard deviation, so right here, so this blue area is about 68%. 2 standard deviations away is about 95%. So that's most of our data falls within 95%. And 3 standard deviations away, almost everything, 99.7% of our data lies there. Now you'll notice 50% of our data lie on one side, 50% on the other. So each of those can be split up. If I had a line here, this one would be 34 and 34 right here. So we could, and then this pink area and this pink area are the same number. This red area and this red area are the same number. So we can use a lot of these things to figure out probabilities, a lot of these properties. You can use the area, the total area being 1. We can use the curve being symmetric, and we can use these facts. So let's talk a little bit now about the standard normal distribution. Now, standard normal distribution is a normal distribution in which mu is 0 and sigma is 1. So we're just here. Looks a little bit boring. And we get a normal distribution without any parameters. So we don't have a mu or a sigma. Mu is 0, sigma is 1, so it looks really nice. Now, x can be any normally distributed random variable, and we can turn it into the standard normal, and that's called standardizing it, using this formula. Z equals x minus mu, and then remember, this isn't kind of an understood parenthesis. When you're doing this on your calculator, you need to go x minus mu, enter, and then divide by the sigma. And this now follows the standard normal distribution. So, how do we standard? So let's look at these 3 distributions we talked about before. And I want you to notice that they all can become this. So if I take every variable in here, every point, so this -3, so this point -3 and minus -2 divided by 1, that's going to correspond to, let's see, -1 over 1 is -1. That's going to correspond to this point on the standard normal, which makes sense because all we did in this green one is it just took the normal, the standard normal distribution, and moved it to the left 2 spaces. So we can see that -3 becomes -1, the -5 becomes -3, everything just got moved over. So it's kind of like a transformation that you might have done in another class. And then the red one, we subtract 3, so each of these numbers gets subtracted by 3 and divided by 1/2. So what happens when we do that? So let's try 4. So 4 minus 3 divided by 1/2, 1 over 1/2, invert the second number and multiply, is 2. So this will correspond to the 2 on the standard normal curve. Which, again, makes sense because this is moved over 3, and by standardizing it, we're stretching it back out again. We're dividing by 1/2, which is effectively multiplying by 2, so we're stretching it back out to be the standard normal. And then take this one. So now, let's take 13. What will 13 be? Well, let's see. We put 13 in there. 13 minus 9 divided by 2. So 4 over 2 is 2. So this one actually also corresponds to the 2. So it's 2 standard deviations away from the mean. So you got 1, 2. Because that's another thing that that standardization tells you. The z tells you how many standard deviations a point is from the mean. And we know that if it's normally distributed and we're more than 3 standard deviations away from the mean, that's a pretty unlikely observation. Unlikely observations occur more than 3 standard deviations away. Okay. So another thing I want to say, standardizing the curve doesn't change the area under the curve. So if I have 2 points, A and B, and I want to find this area, then just because I smish it in a little bit and move it doesn't change the area. I can standardize A and B, and this area is exactly the same. It does not change. So this areas under the curve, I want to say that again, are probabilities between points. So this is the probability that X falls between A and B, or the percentage of the data that is between the points. So the percent of all X's that lie between A and B can be found using this area or this area, since it's exactly the same. So let's consider a normally distributed random variable X. So X is normally distributed with a mu of 61 and a sigma of 9. Now, how would you generally standardize this thing? How would I should the, I should say, okay. How would I show the, I should say show, not should. How would I show the general standardized version of this? So remember, it's X minus mu over sigma. So generally, we don't have an X to plug in, so we're just going to keep X there. Z equals X minus 61. So just plug in your mu and your sigma. This is the general standardized version. So if I'm given any point on this normal distribution, I can find the standardized version simply by subtracting 61 and dividing by 9. Now the area under this normal curve between 50 and 70, so let's make this normal curve real quick. Here's 61, and the standard deviation is 9, so let's go 70, 79, and 88. And over here, minus 9 will be 52. And over here will be 43, and over here will be 34. So I've got 3 standard deviations on either side. So this is going to look, here's the middle, 61. So this is going to look something like this. Okay, that was terrible, but not bad. Okay, so 50 to 70. So we're looking at somewhere in here to here. So we're looking at this area right here. And that corresponds to what z-scores. So we need to find what these are going to be. So this corresponds to the area under the standard normal. Here's the standard normal, 0, -3, +3. So let's standardize this. Z is 50 minus 61 over 9, which is -11 over 9. And Z is 70 minus 61 over 9, which is 1. So we're looking at 1 over on this side. And on the other side, I could have 11/9. So just past 1 a little bit, -11 over 9. And we're looking at this area, which if I would have drawn this better, it would look the same. So if I want to find the area under this normal curve less than 75, what z-score and in what direction? So again, here's our 61. Our 75 is about right in here somewhere. And I want to know what's the area under this curve for x less than 75. So I want this area right here. So I would want the area to the left of 75, or area under the standard normal under 75 minus 61 over 9, which is, see, that's 14 over 9, which is about, what, 1 5/9 or so? So I can convert these, and I can find these very, very easily. And again, the z-scores tell me how many standard deviations a point is away from the mean. So let's talk about finding areas under this standard normal curve. So again, here are 4 different things we want to look at. Shaded area here is an area to the left of some z that we have. I might call this z star, just so that we have a difference. So the area to the left of z, the probability that capital Z, which is the standard normal, is less than z star, we're going to use something in your calculator called normal CDF. We always use CDF with normal. Normal, always use CDF. The PDF is only for graphing. It doesn't actually give you probabilities. It gives you the probability density. So shaded area, area to the left. So what we have, we look at this, and I'm put -10 in here. But really we're going, I just do -10 because at that point we're pretty much negative infinity. You can pick any number that's 5 standard deviations less than 0. 5 ones less than 0. You could pick any number. This 10 could be pretty much be any number less than -5. Sometimes I like -99. It's just a habit that I get into is -99. I don't know why. I don't know. I picked that. It just makes sense to me. Now, an area to the right. Now, we're greater than our z star. So now, normal CDF, we want to go from the z star to positive infinity. And again, this can be anything over 5. Sometimes I like to use 99. I put 10 in here. It doesn't make any difference, really. So an area between 2 points, z1 and z2. So here we're just going to do the normal CDF from z1 to z2. That's how normal CDF works on your calculators. And let's say our shaded area is an area to the left of z1 or to the right of z2. So that looks kind of like this. It's an or we can also call it a union. Well, isn't this just the whole thing is 1? So this is 1 minus the area between. So we take the area between here, we subtract that from 1, which is the whole, and we get the shaded area. You could also find these shaded areas separately by taking the area to the left of Z1 plus the area to the right of Z2. That would be another way to do it. And again, there is no probability attached to any single value of x. That is the probability that x, that should say capital Z and little z. So let's say I want the probability that z is 1. That's pretty much 0. It does not have a probability. I would have to do the probability that I'm between 0.9 and 1.1. And you'll notice something that I'm doing here. I'm kind of using less than or equal to and less than, greater than or equal to and greater than. I'm using these synonymously. So that's because since there's no single probability attached to equals in continuous distributions, these two things are not different. It doesn't matter if you say less than or equal to or less than. It doesn't matter if you say greater than or equal to or greater than. There's just no difference between these two, and there's no difference between, of course there's a difference between less than and greater than, but there's no difference between less than or equal to and less than, and there's no difference between greater than or equal to and greater than. So let's practice doing this. Areas to the left, we use normal CDF. So let's practice this. We go into your calculator, and I do expect you guys to kind of follow along. Grab your calculator, and let's take a look at what we're doing. So we're going to use normal CDF. You find normal CDF under second vars. It's under your distributions. It's the second one. You can even hit the 2. And those of you who come up with a menu, it says lower, upper, mu, sigma, and paste. Now, those of you who do not come up with a menu, you're going to come up with something that just says normal CDF with a parenthesis. So you're actually just going to plug in. We're just going to do the same thing. Notice it's giving me -1 E99. That means it's giving me -1 with 99 zeros behind it. Is that less than -10? Yes. I don't even need to change that. So I'm going to go down. If you just have this, you can go ahead and type in -10. And then you plug in the number that you're talking about, -1.55. So our upper is -1.55. Now, 0, 1. Now, those of you who don't have a menu, don't worry about that because you do not need to put a mu and sigma in there. The mu and sigma default is 0 and 1. We don't need to change that for our problem. We're just going to hit paste and enter. And you should get 0.0606. Again, go 4 decimal places for these probabilities. Okay, let's try another one. 0.9. Normal CDF. From negative that, our upper is 0.9. Enter. Enter. You should be getting 0.8159. So once again, let's try it again. Now we need to go up to 2.14. And that's 0.9838. And then let's do this final one. It is -0.18. Oops. Oops. Sometimes that likes to pop to the other side for no reason other than it just likes to do that. Oops. I messed that up, so I'll just plug in -10. -0.18. Okay, and you should have 0.4286. So let's draw a picture of what we're doing here. So remember, we have the normal distribution. -1.55 is going to be, here somewhere, right? About halfway between. So we want this area, oops, that's positive. So we want, sorry, negative 1.55. So we want the area to the left of it. So we want this area right here, which is 0.0606. Kind of makes sense. It should be a small area. It should be, these areas to the left of the negative numbers should be less than 0.5. And if we're over here, so say this is 0.9, notice this is greater than 0.5. And here, 2.14 should be most of it, should be close to 1, and it is. Negative 0.18, this is really close to 0. The area to the left of 0 is 0.5, so this should be really less than 0.5, but close. And it is. This one should be close to 1. So we can see how these answers even make sense. So that's something you want to do. Does your answer make sense? And I always say, when in doubt, draw it out. I know that sounds really cliche and rhymey and weird, but if you aren't sure, draw a normal curve and label. I don't require it, but it's a nice thing to do if you're a little bit confused on what's going on. And I don't mind having a whole bunch of normal curves all over your paper. That doesn't bother me. So let's talk about areas to the right. So we did area to the left of 0.9. What is the area to the right of 0.9 going to look like? Think about that. That's got to be less than 0.5. So it's less than 50%. So let's put that in. So we're going to go second vars, number 2. And now our lower bound starts with 0.9. So we're 0.9 up to infinity. And whatever, 10 is good enough. And we get 0.1. And I want you guys to be very careful about your rounding off. This is 0.1841 because the next number is 5 or more. So and that makes sense, right? And I also want you to look at this thing. When we had the other side of 0.9, we had 0.8159. Notice this. 0.8159 and 0.1841. What does that add up to? 4 zeros, but that's okay. It ends up to 1, which it should, because this side and this side should equal 1. If I have this whole area plus this whole area is the whole area under the normal curve, which should be 1. So that's kind of cool. So we could have actually just done this by going 1 minus this particular problem right here. So let's look at 2. What's the area under the standard normal curve greater than 2? So let's go back to my distributions, number 2. So now I'm 2. And I have 0.022875, whatever. And so what happens when I'm 1.85? So let's see, we can 1.85, paste. And that's a little bit bigger, which it should be 0.0322. Okay, let's move on. Okay, let's talk about areas between. Areas between, super simple. I'm going to draw this first one out for you. Negative 1.55 to positive 1.3. It's a pretty big area, right? Should be a pretty big number. So let's find out. So here, we literally just put in our first number, negative 1.55, whoops. And I also want to point out, I think you probably have this by now, but make sure your negative, when you say something's negative, you use this key down here, whoops, and not the minus key. This is for subtracting, this one's for making something negative. And 1.3. Paste. Okay. So here we have 0.8426. Yep, it's fairly high. Not everything. It's 84.26%, so that's not bad. Let's look at this next one. Normal CDF number 2, negative 0.68 up to 0.56. That is going to be 0.4640. The next one, now this one's all on one side. These are both positive. So this is from, well, that's terrible. That is a bad one. There we go. So this one's from 0.2, so just about right here, to 1.2. So this is this area. So note, this is going to have to be less than 0.5. It's all on one side. 2, 0.2 up to 1.2. Yep. 0.3057. So negative 0.25 to 0.25. So that's going to be like here to just here. So we're going to have number 2, negative 0.25 up to positive 0.25. And enter twice, and we have 0.1974. So, not too bad, right? That's within a quarter. Remember that z-scores is how many standard deviations you wear from the mean. So we're a quarter of a standard deviation away from the mean, and about 20% of the data falls there. Just kind of an interesting thing. So let's do an example of areas away from the mean. So remember, in this case, we want to go 1 minus the normal CDF, area between these two. So when I'm looking at this guy, here's negative 0.53, here's 1.6. I want this area out here, and I want this area added together. So what I'm going to do is I'm going to take 1 minus the area in here. And so to do that, I can start by putting 1 minus on there before I go. Distribution, number 2. I want to go from negative 0.53 up to 1.6. And I have 0.3529. Let's do this one. 1 minus normal CDF from negative 1.99 to negative 0.26. Again, this is on the same side, so the area between is going to be less than 0.5. So our answer should be more than 0.5. It is 0.6259. Because if you think about that one, here's negative 1.99, here's negative 0.26. We want this whole thing plus this little tail. So definitely going to be more than 0.5. Okay, so now we need to talk a little bit about working backwards. Now sometimes we're given the probability and we need to go, well, what z was that? So let's take a look at this. Now in this case, what we have is we don't know the z-score. Now this is where you kind of have to know things about this. Area to the left is more than 0.5, so it's got to be over here somewhere. This is where the z has to be. Because half of it, this is 50%, is to the left of 0. So we know that it has to be more than 0, so positive. So we know it's on this side. And we know that this area is 0.6232. Well, we have something for that. We have something called inverse norm. Now, when you use inverse norm, your calculator assumes that you're telling it an area to the left. Now, a few of you, those of you who have that are using Casios, or there's I think the TI-84, the newer ones, the CSE or something like that, CE or something like that, actually allows you to change this to where you're going to do left, right, or center. I'm going to assume that everybody's doing left right now, but if you have that ability, you can definitely change that. So for the rest of our calculators, it assumes that we have an area, we're giving it an area to the left. So what we do is we use inverse norm. So we go second, and inverse norm is number 3. We tell it this area, 32, and we're still got mu and sigma we're still in the standard normal, and 0.31, so z is 0.31. Now in z-scores, 2 decimal places is fine. I know it seems confusing, but this way it helps keep it straight, because this looks like a probability, but it isn't. This is actually the point on the z-score. So if z is about 0.31, the probability that we're less than that is about 62%. So let's do this next one, 0.072. So where do you suppose that's going to fall? Really tiny probability. So it's probably going to fall, it's got to be negative. It's got to be over here somewhere. So, because this little area is only 0.072. So let's do our inverse norm again. And those of you who just get inverse norm with a parenthesis, you're just going to plug this in. So 0.072, enter, and we have negative 1.46. So this point is negative 1.46. It makes sense. So now, what about 0.995? That's almost 1. So that's going to be way over here, because this whole area right here is 0.995. So we're going to have a z that's just got a teeny little tiny tail over here, because of course that tiny tail is going to be 0.005, because it's 1 minus this. So it's going to be this little tiny tail. So let's go ahead and put that in there. Inverse norm of 0.995. And we have 2.57. I'm going to go ahead and put 3 decimal places on this, because I don't want to do 8, so I'll do 576. Kind of just the way that it's done. So that one's 2.576. So it makes sense that it's close to 3, because it's way over here. Most of the data is to the left of it. 99.5% of it is. So examples using inverse norm, area to the left, because your calculator assumes you're giving it an area to the left, most of you anyway, when you're given areas to the right. So we have a little bit of a notation I want to talk about. I have this z sub alpha, where alpha is an area to the right. And in order to find z sub alpha, I need the probability that z is greater than z sub alpha equals alpha. So if I want if I just want to find z of 0.05, let's say, then I want the probability that that z is greater than z of 0.05 is 0.05. However, remember, inverse norm assumes an area to the left. So we want an area to the right of being only 0.05. So if this area to the right is 0.05, then what's the area to the left of this thing? The whole thing's 1. So this has to be 0.95. So I can put an inverse norm of 0.95. So let's do that. Inverse norm 0.95. And we get 1.645. Again, I go 3 on that one just because it looks better. And then now I want z sub 0.1. Same idea. This means the area to the right is 0.1. This is just a notation. Area to the point is 0.1. So I want to use inverse norm at 0.9. Oops. Not 0.1, because 0.1 is going to give me the negative of it over here. So I want inverse norm of 0.9. And that is 1.28. I think that's fine. Okay, so let's say that I screwed up and I accidentally put in 0.1 here. What do you think would happen? Remember, this is symmetric around 0. The standard normal is symmetric around 0. I will get negative 1.28. So just kind of something to kind of watch for while you're doing this. If you get negative when you're trying to find these z of point something, especially if it's less than 0.5, it should be a positive number. So if it's more than 0.5, well, then it should be a negative number, so it would be fine. So let's find 0.99. So let's go inverse norm 0.99, and we get 2.33 is fine. Okay, so this, don't be scared of this. This is just notation. Z sub alpha is just the z where alpha is an area to the right. So you want to find inverse norm of 1 minus alpha. That's all you have to do. Okay, so this is a little more difficult. We are given an area in the middle, and we need to find what these z's are. Now here we call them a's, but that's okay. I call them a's down here. I'll call them a's up here. Doesn't really matter what I name it. So we want the probability that negative a to a is 90%. So this is 0.9 in the middle. So the question is, what's the area in the tails? Well, it's 5% or 0.05. You notice what I said up here, 1 minus alpha over 2. Okay, so I said 1 minus the area divided by 2. That's how I find my area in the tails. So this 1 minus 0.9 is my total tail area divided by 2 to get my area in each tail is 0.05. Now what I can do is I can use inverse norm of 0.05 to get this area, to get this, or this area is 0.05, to get this number. So if I do that, inverse norm 0.05, then I get negative 1.645. And now let's find this one. Now we could also say this is negative a, so this is positive a, and that is a true statement. We won't be able to do that when we leave the standard normal distribution. This is only because this is symmetric about 0. When I'm symmetric about 10, it's not going to work. So another way to be able to find this point is, remember, area to the right is 0.05, so the area to the left must be 0.95. So this whole area right here is 0.95. So for this one, I would use inverse norm of 0.95, which we've already done. Okay, so next time we'll start talking about other normally distributed variables.